Good evening, everyone. Thank you for attending this webinar from the Quantum Spain Talent Q program. You know that these are webinars that we produce monthly. And today we have the pleasure to have Zoe Holmes from EPFL from Switzerland. She is physicist. She was awarded with the master degree in physics and philosophy from the University of Oxford. Later, he was studying in Imperial College of London. And later, he was working as postdoctoral research in Los Alamos National Laboratory. Currently, she is working in this problem, Barren plateaus, that is a problem in the parametric quantum circuits for quantum computing. And I hope you enjoy this seminar to learn which is the problem and which I hope the solution of this big issue in parametric quantum circuits. So the floor is yours.
Cool. Thanks for the introduction. I don't think I'm going to solve anything today, but hopefully I can at least set out some problems and some directions I think are interesting. So yes, the title of my talk is Does Provable Absence of Bound Plateaus Imply Classical Simulability? And I've put in the subtitle a genuine question because it is a genuine question. I don't have a definitive answer to give. I have a sort of yes-no answer to give. Okay, and so this was a collaborative paper with a large team of people. And I just really want to highlight that many fun arguments were had in the making of this work. So it was impossible in the end to come up with a text where we all agreed with every line of it. Because some of the things we have to say are provable, well-defined facts, but some of it is more discursive. And once you get into discursive territory, trying to get, I don't know, 10, 11, 12 authors to agree is practically impossible. And that's how I think you should interpret what I'm sharing with you today. Some of it will be things that we understand well, things which are factual, but some of it is discussion points. So I really hope afterwards we can have a nice discussion. And actually, if you have any burning questions as we're going through, feel free to interrupt me. Talking for 45 minutes, just hearing my own voice, is not as easy as it was during COVID days. We got used to interacting more. Cool. Okay, so let me get started. So the focus of my talk today is hybrid variational quantum computing. Now, this is a very broad paradigm, so let me just clarify here and now that for the purpose of this talk, I'm going to focus on any method that optimizes a parametrized quantum circuit by minimizing a quantum cost function, potentially using training data. So this encapsulates variational quantum algorithms and many, but not all, quantum machine learning methods. Now, I feel that this slide is a little bit superfluous because if you are listening to this talk and are interested in this talk, you probably already know what variational quantum algorithms are. Nonetheless, I feel it would be rude not to at least attempt to give a summary for a couple of minutes, so that's what I'm going to do. So the core idea of a variational quantum algorithm is to pick a faithful loss and parameterized quantum circuit, or QNN, I'll use these terms interchangeably, such that if successfully trained, the optimal parameters, circuit, or cost are in some sense an approximate solution to whatever problem you're trying to solve. So your parameterized quantum circuit is just a quantum circuit where some of the gates are parameterized. So they're parameterized rotation angles standardly. You then run your circuit with respect to a particular set of parameters. You then perform a measurement. Your circuit and your measurement is designed such that this gives you your cost with respect to those parameters. You feed your cost with respect to those parameters to your classical computer. Your classical computer runs your favorite optimization algorithm, gradient descent, Bayesian optimization, your favorite black box SciPy optimizer that if you're entirely honest, you're not entirely sure how it works, but seems to do the trick. You get whatever optimizer you run, you then get the parameters to try next. You feed those parameters back to your quantum computer. You then run your quantum circuit with this new set of parameters. That gives you a new cost, and you just keep on looping around using this hybrid quantum classical optimization loop to try and minimize your cost. And your optimum parameters, circuit, or cost, once found, will be in some sense an approximate solution to your problem. Okay, and in what follows, I'm going to focus on costs or losses of this form. So that is, you have some initial state, you evolve it under some parameterized quantum circuit, and then you measure some observable. But generalizations of this cost, where you sum over different initial states and observables or do some classical post-processing, similar conclusions to what I'm going to argue also apply to those. And a warning or apology, I'm going to use the terms loss and cost interchangeably because, in all honesty, I could not be bothered to try and make my slides consistent. Okay. So this is, as I'm sure many of you are very aware, a hugely popular and flexible framework that has been applied to all sorts of different areas over the last 5 years. Okay, but despite the popularity, people soon realized that actually training these algorithms was quite hard. Okay, so there are different reasons why training can be hard. So you can have expressibility or expressivity limitations, which is roughly how likely it is that your parameterized quantum circuit contains a solution. You can have issues due to small loss gradients or small loss differences, and you can have issues due to local minima. My focus in this talk will be just on loss gradients and loss differences. Okay, so at its core, hopefully it is clear that you're going to need to have a loss landscape to be sufficiently featured in order to be able to train. That is, you're going to need to actually have substantial gradients in order to be able to train your loss based on these gradients or cost differences in order to try and minimize your cost. And note this is particularly an issue in the context of trying to minimize a quantum cost, because if you have small gradients, then you're going to need high precision measurements to find the loss minimizing direction. But a quantum loss is only ever measured statistically. So that is, you measure it by running your circuit many, many times and performing lots and lots of measurements. So using lots and lots of shots. So specifically, 1 over sigma squared shots are required to estimate a loss to precision sigma. So if you've got small gradients and need high precision measurements to find a loss minimizing direction, you're going to need lots of shots in order to determine this loss minimizing direction. So that is, if you have very small gradients, it becomes resource intensive to train. Okay. So there is an increasing awareness of the so-called bound plateau phenomenon. So the bound plateau phenomenon is when people can prove, and I'll show you how and when in a little bit, that the variance in the partial derivative of the cost vanishes exponentially with the number of qubits your circuit acts on. So little n here is the number of qubits on your circuit. If you combine this with Chebyshev's inequality, what you get is that the probability of observing non-negligible cost gradients vanishes exponentially with the size of the problem, because this probability is determined by that variance. So for small scale problems, i.e. small n, problems that we can handle currently to try and simulate them on our laptop or on available quantum devices, you may actually have reasonably large gradients. But as we get to more and more interesting problem sizes, the type of problems that could actually, problem sizes that could actually solve interesting problems, the type of problems that we can't simulate easily on our laptops, then our landscape is going to get flatter and flatter. And as our landscape gets flatter and flatter, we're going to need higher precision measurements in order to determine cost minimizing directions. So that is, if your variance decreases exponentially, the shots required for training is going to typically grow exponentially with problem size. This is the bound plateau phenomenon. Note you can also frame this not in terms of the variance of the partial derivative of the cost, but also directly in terms of the variance of the cost. And mathematically, this often makes things simpler. Okay, so the bound plateau phenomenon was first discovered by Jared McLean in the seminal paper back in 2018. So here he showed that using an inappropriate choice in parameterized quantum circuit, namely using one that was too deep, effectively a polynomial depth random quantum circuit, then you end up with a bound plateau. We later sort of pinned down this connection a bit further, and we draw a connection between the expressivity of an ansatz and bound plateau phenomena. So we showed that if you have an ansatz that's too expressive, you end up with a bound plateau. This paper then showed that if you have an ansatz that's not necessarily too expressive, but it leads to states that are highly entangled, then this can lead to bound plateaus. Intuitively, this is because if you have a highly entangled state and you're then going to measure some local observable, your reduced state just on that single qubit is going to be close to maximally mixed, and it's going to be close to maximally mixed for all parameter settings, and so you're not going to have much variance as you change your parameter settings. In this paper here, we then showed that actually using, even if you have a really good choice in quantum circuit, there can be certain problems, namely ones that are too random, that lead to bound plateaus. So we showed that you can have bound plateaus when trying to learn typical random unitaries or equivalently typical scrambling unitaries. Then there was this seminal paper by Marco Cerezo where he showed that the choice in cost function could lead to bound plateaus. So namely for random brickwork circuits, so sort of random brickwork circuits, if you have a global measurement, even at very shallow depths, so even order 1 depth, even with a single layer of random unitaries, you can end up with a bound plateau. But if you have a local cost, then for deep circuits, you're going to have expressivity and entanglement-induced bound plateaus. But for shallower circuits up to log depth, you cannot have bound plateaus. And then Samson Wan et al. Showed that noise can also induce bound plateaus. So historically, this analysis grew in a sort of piecewise basis. Many of these different causes of bound plateaus have recently been tied together in these 2 nice papers by Enrico and Michael, where they tie them together in this sort of dynamical Lie algebraic approach. Okay, so in parallel to this research on the different sources of bound plateaus, there's also been a parallel line of research looking into provably bound plateau-free strategies. So the first of these we've actually already seen on the previous slide are shallow hardware efficient ansators with local costs. This is random brickwork circuits at log depth with local costs. Then we have quantum convolutional neural networks. So these are log depth circuits that basically have pooling layers where you measure out qubits and combine the results and feed them forward. Then we have symmetrized ansatzer, so certain Hamiltonian variational ansatzer, certain permutationally equivariant quantum neural networks, ones where you use correlation, you use symmetry to simplify your problem. So these can also, in certain cases, namely ones where your generators live in a polynomial dynamical Lie algebra, can lead to can provably not have bound plateaus. One thing I should have highlighted. What I mean here by proving they don't have bound plateaus is that the variance in the partial derivative of the cost, or just the variance in the cost, scales at worst polynomially. So you can lower bound the variance in the cost and show that there's a 1/poly lower bound. Finally, small angle initializations. So initializations close to identity, these can be proven to be provably bound plateau free. So have variances that scale at worst polynomially. Okay. So that was a lot of references in quite a short period of time. That was because this field grew in this piecewise manner. What I want to address in my talk today is whether there's a common story to be told, and if so, what is the consequence of that common story? Okay, so to discuss this, let's go back to the start and look again at our loss. So our loss here is, as we said, we take some initial state, we evolve it on some unitary, and then we measure some observable. And the key thing to note is that this is an inner product. So it's an inner product between the Schrödinger evolved state and the observable, or equivalently, just swiddling things around, it is an inner product between the initial state and the Heisenberg backpropagated observable. Now, this should immediately raise red flags because it is an inner product between 2 exponentially large objects, and the inner product between 2 objects that live in an exponentially large space will typically, unless you align them really nicely and cleverly, be exponentially small and concentrated. So this is claim 0. Bound plateaus effectively arise from a cursor dimensionality. We're looking at the inner product between objects that live in an exponentially large space, and this will typically just be 0, typically be concentrated. Note that the word typically here is doing quite a lot of work. Okay, so let's dive into this in a little bit more detail and ask, when does this cursor dimensionality kick in? Okay, so to do this, we're going to think of the observable as some sum of some terms p lambda, and we're going to ask, where can this observable go when we backpropagate it? So when can we and when can we not explore an exponentially large space? And these questions can be answered by computing the inner product between our Heisenberg evolved observable and p lambda for all the elements in the base of the Hilbert space. So I'll spell this out more in a second. I think for now, let's just think about this really pictorially. So imagine our observable is already global. So we have some global Pauli, for example. Then imagine we have a short depth circuit right next to it. In fact, just a single layer will do. Just a single layer of single qubit rotations can turn this global Pauli into any other global Pauli. There are exponentially many global Paulis, so that is your observable already lives after being Heisenberg backpropagated in an exponentially large space. On the other hand, suppose you have some local observable. If you have some local observable and you Heisenberg backpropagate it, then because of light cone effects, it's going to be confined to some relatively small region. So it's going to be confined to log n qubits. And now if you're even order 1 qubits, depending on the depth here. And if you're in some confined region, in this confined region, you will only have polynomial many Paulis in that region. Because if you have a local Pauli here, there are only polynomially many local Paulis. So that is, if you have a shallow depth circuit and a local observable, you're not exploring an exponentially large space, you're exploring a polynomial space. On the other hand, if you have some local observable and you backpropagate it through some deep circuit, eventually you're going to have your light cone reaching the full width of your circuit, or at least order n different qubits. And once you're there, you're again going to be back to this global case. You're going to be able to produce all global Paulis or many global Paulis, and then you're exploring an exponentially large space. So the key message here is that both circuit depth and structure determines where we can go, but also the observable. It's the combination of the circuit depth and structure and the observable that determines the space in which the back Heisenberg propagated observable lives. And it's this space that determines whether or not you're concentrated. Okay, so this is effectively a pictorial reinterpretation of the results in Marco's cost function dependent bound plateau paper. Okay, so let's make this a little bit more mathematical now. So we're going to take our loss and we're going to take our observable. Our observable is going to be written in terms of a sum of these p lambda terms. And I'm just going to substitute it into our loss here. So now our loss is a sum of the inner product between rho and the Heisenberg backpropagated p lambda terms. So we've got some p lambda, and we're going to have some Heisenberg backpropagated p lambda of theta. And now let's suppose this p lambda of theta lives in some subspace b lambda. Then when we look at this inner product, we can compute this inner product just by projecting the state rho down to that subspace. So that's what rho lambda is in this expression here. So that is, we see that the loss is a sum of the inner products in each subspace. So that is a sum of the inner products of the subspace in which each of the Heisenberg backpropagated terms of the observable live. Now, if any of these subspaces is only polynomially large, then the loss can be non-concentrated. However, crucially, actually, that is a necessary condition, but it's not a sufficient condition. Or no, more carefully. Okay, this is the precise statement. If any of those subspaces is only polynomially large, then it can be non-concentrated. However, that alone does not guarantee it is non-concentrated. The initial state is also important. So if rho is too entangled, i.e., in particular, if it obeys a volume law, that when you do this projection down onto this subspace, where this subspace we're assuming is polynomially large, not exponentially large, then your reduced state on that subspace will be close to maximally mixed. And so again, you're going to lose any sigma. The loss is going to be exponentially concentrated. So we see that rho must not be too entangled. It must satisfy an area law. And this is effectively a reinterpretation of the entanglement-induced bound plateau results. So it's not just the initial measurement and the structure of the circuit that matters. The initial state is also really important. Okay. So this is the second claim I want to make. When we have a provable absence of bound plateau, it is because we have confined the problem to live in a polynomial subspace. And we can see this by a case-by-case analysis. So I appreciate this table is a lot to take in. I'm including it more for those of you that are very on top of this literature than sort of the average person in the audience. But the main thing I want to highlight is that we can go through all of these cases that I basically showed quickly a couple of slides back, where people have proven the absence of a bound plateau. And we can show that in all of these cases, the way in which the circuit they are advocating manages to avoid a bound plateau is effectively by confining the problem to a polynomial subspace. And crucially, this is a classically identifiable polynomial subspace. And it's actually the very proof of the absence of bound plateaus that allows us to find these polynomial subspaces. And note, this is actually an important caveat I'll come back to later, because it's the provable absence. It's the proof that allows us to find the subspace. You could actually have architectures which have polynomial gradients, so have substantial gradients, but we don't know how to prove it, and we don't know how to find the subspace. Okay, but as I'm sure many of you will have guessed, if these proofs of absence of bound plateaus manage to avoid bound plateaus by confining the problem in a polynomial subspace, then we're sort of faced with the problem of classical simulability, because isn't the whole advantage, or one of the major advantages of quantum computing, the thing that's meant to make quantum computing more powerful than classical computing, the fact that we can't simulate it easily classically, is because we live in exponential subspaces. So if we've actually just made the problem live in a polynomial subspace, it is natural to ask whether can we actually just classically simulate those cases. Okay, so before I get there, I just want to pin down 3 different definitions of classical simulability that we're going to discuss. So we're going to have standard classical simulability. This is where the whole problem is just done classically. We're going to have QSIM, so that was CSIM. We're then going to have QSIM. Now, QSIM is the standard hybrid variational quantum computing framework. So this is where you measure your quantum computer, you measure your cost on the quantum computer, then you send your cost function value to the classical computer, and then you keep on going around in an optimization loop until you minimize the cost. Okay, so QSIM, basically standard variational quantum computing. And then we're also going to introduce this third framework, which we call CSIM-QE. So quantum assisted, quantum enhanced classical simulation. Note, we had many debates on what was the best name for this. You could also call it quantum surrogating, because the idea here is rather than having an adaptive hybrid quantum classical loop, you are going to, at the start of your problem, collect a bunch of data from your quantum computer. So this could be, or standardly might be, a classical shadow type protocol. You do a bunch of Pauli measurements on some initial state. And then once you've collected that data, you're no longer allowed to interact with your quantum computer, and the rest of the optimization is done classically. Okay, so a quantum advantage is possible for any problem that is neither QSIM or CSIM-QE and not CSIM. So any problem where you actually need to use the quantum computer at some point. A quantum advantage, or an advantage from running the parametrized quantum circuit itself, is only possible for problems in QSIM and not CSIM-QE. So an advantage from actually doing the standard VQA algorithm, or at least an exponential advantage, is only possible if it's in QSIM and not CSIM-QE. Okay, so let me go back to the case-by-case analysis. So I've claimed that provably bound plateau-free architectures live in classically identifiable polynomial subspaces. And then what I want to highlight is that in each of these cases, as you might expect, the parameterized quantum circuit can be classically simulated. And so the loss can be classically simulated if the initial states and measurements are classically similar. So in all of these cases where people have proven the absence of bound plateaus, if the initial state and measurements, if everything else involved is classically simulable, then these things will also be classically simulable. So note, I'm not really saying anything new here. I think this was sort of increasingly discussed in the community, but it wasn't really highlighted, arguably, in these papers that prove the absence of bound plateaus in various circumstances, and arguably it hasn't fully sunk in still in all corners. So just to sort of spell this out a bit quickly, things like the shallow hardware efficient ansatz, these are sort of random brickwork circuits, quantum convolutional neural networks, small angle initializations, some cases of quantum generative modeling. These can all be simulated using tensor network type methods, at least in the regimes where we can prove the absence of bound plateaus. That's a crucial caveat. You can also use light cone based methods, where you basically ignore stuff that is outside of the light cone that is relevant. And potentially these can also be simulated using Clifford plus tree methods. This is something that we're particularly excited about in my group at the moment. But I should highlight that in contrast to these other cases where you can prove that these methods are going to work, you can have bounds and guarantees. We don't fully have those in these cases. Okay, and then all of the sort of symmetrized ansatzer, where people can prove the absence of bound plateaus, these can be simulated using sort of DLA, dynamical Lie algebra based simulation methods, such as GSIM. There's a whole bunch of different papers doing this in different cases. Okay, so for all of these cases where we can prove the absence of bound plateau, if we have classical initial states and measurements, then we have classical simulation methods. And as I said, there was nothing really new to what I'm saying here. This was increasingly discussed, but arguably hadn't sunk in all corners. But I used to say, at least, and I think a lot of us did, for non-classically simulable initial states and measurements, then you're going to need to run the variational quantum algorithm on a quantum computer. So yeah, sure, if you have classical initial states and classical measurements, and U of theta can be classically simulated, then the whole problem is classical. But I used to say that if the initial states and measurements weren't classically simulable, then we'd need the quantum computer. And it's true, you do need the quantum computer, but crucially what I want to highlight to you is you don't need to actually run the variational quantum algorithm on the quantum computer. And this, hopefully you can see from what I highlighted earlier, the key point is that if the Heisenberg backpropagated observable lives in a polynomial subspace, then we can just project the initial state down onto that subspace and then simulate the rest of the VQA classically. So let me just recap this. So what we said was that we had some observable that we were going to write as a sum of different terms. And we're going to define B of lambda as the subspace in which each of the back-propagated P lambdas live. And then our loss is just the sum of the inner products in each subspace between our initial state projected down onto the subspace B lambda and our back-propagated observable. So to simulate this loss, all we need to do is to compute a basis for these subspaces and then project the state onto that basis. So if we have a classical representation of our initial state, we can do this projection classically, and then the problem is in CSIM, the whole thing is classically simulable. And if we do not have a classical representation of rho lambda, then we can do this projection on a quantum computer using tomographic protocols. So for example, if we're looking at just local Paulis, it's just going to require classical shadows, local classical shadows, or even just standard basic state tomography to get those local Pauli measurements and project rho lambda down. Okay, and crucially, as I said, for provably bound plateau-free architectures, these things live in polynomial subspaces. So this projection process only takes a polynomial number of measurements. And this means the problem is in CSIM-QE. So that is, it can be done using quantum-assisted classical simulation. So it can be done by gathering some data from your quantum computer initially, and then simulating the rest of the variational quantum algorithm classically. Okay, so yeah, the example I had before, if we're working with a shallow hardware efficient ansatz, then you're just going to measure basically Pauli, polynomial number of Paulis acting on log n neighboring qubits, using standard tomography methods or classical shadows if you prefer, and then you can simulate the evolution using reduced light cone methods. Okay, so this comes to claims 2. If we do a case-by-case analysis of all bound plateau-free architectures and methods currently used in the literature, we see that problems in known polynomial subspaces are classically simulable, but if you have non-classically simulable initial states and measurements, you'll potentially need to first collect data from a quantum computer. And again, this table contains a lot of information, but the key thing I want to highlight is that in each of these cases where people have proved the absence of bound plateaus, we can identify both the tomographic procedure for the projection and the simulation algorithm itself. This column I'll come back to in caveats in a second. Okay, so punchline is that in none of the standard instances where people can prove the absence of bound plateaus, does the parametrized quantum circuit actually need to be implemented on the quantum computer in order to estimate the loss in polynomial time. Okay, and I just want to highlight that this has a flavor of earlier work by Robert Huang on power of data in quantum machine learning, where he argues that if you have a classical learner, but with data from a quantum computer, this is a very powerful setting. That's essentially, to some degree, what we are also arguing here. Okay, so where does this leave us? I think there are many different ways in which we can approach this. And now I'm going to spell out some of sort of the caveats and new opportunities in these arguments. So first thing I want to highlight is that a quantum computer may still be crucial. So if we are working with a problem where our initial state is non-classically simulable or our measurements are non-classically simulable, if we're working with an inherently quantum problem, then a quantum computer is very much still needed to collect data. Though, of course, as I said, this is only if the initial state and measurement is quantum. If you are dealing with sort of classical data problem and a classical initial state, then actually I think our conclusions are a much bigger problem. So a quantum computer is very much still needed to collect data, but crucially, it's used differently. It's used non-adaptively to create a surrogate, which is then used for training. And I think the advantages and disadvantages of surrogating versus running on hardware can become blurred at times. So I think there are some cases where it's clear you just need to get local Pauli measurements of your state in order to then do your surrogating, where it seems like surrogating is the way forward. But there are other cases, for example, where you have some deep, sophisticated quantum circuit and just a few parameters that you're changing throughout it, where it's not so clear, actually, whether or not you're going to want to surrogate versus just run the VQA standardly. It's also not clear necessarily which is going to be more efficient. So here we're comparing polys and polys. So we're saying that you can do your surrogating with a polynomial amount of data from your quantum computer, but also your VQA, you're only ever going to run it using a polynomial amount of data. So I really think there's sort of interesting directions here to investigate surrogating versus standard VQA approaches. And there may well be provably poly or practical advantages from not surrogating and actually running on the hardware. Second point is this is a case-by-case, not absolute argument. So we can actually construct counterexamples of non-concentrated losses that are not classically simulable. We do this using sort of cryptographic hardness assumptions, effectively smuggling in the discrete logarithm problem. But I want to highlight that these examples, so we have one in the appendices of our paper, do not resemble current mainstream variational quantum algorithms, and it's, to be honest, very, very contrived. But I think we can still learn things from these observations. Effectively, it breaks the assumption that comparing objects in exponentially large spaces leads to concentrated expectation values, because crucially, these circuits are structured. So I said at the beginning, we have this red flag. We're looking at the inner product between objects that live in an exponentially large space. This will typically be small, but typically is doing a lot of work there. It need not be small if you can explore the space in a clever way. And this is actually what standard fault-tolerant algorithms do. They're not randomly searching a space, but they are cleverly manipulating objects in an exponentially large space. So I think it'll be interesting to investigate using more fault-tolerant inspired algorithms within VQAs. I think this is another interesting direction to explore. Okay. Third caveat. Our argument applies to losses of this form. So initial state, parametrized quantum circuit, and then some observable. It also applies a bit more generally to sums of terms of this form or some post-processing of terms of this form, classical post-processing. But not everything, not all losses that we can dream up do fit in this form. So one example would be Boltzmann machines. So I think there's also wiggle room here to investigate other learning paradigms, other losses that use different losses. Though the thing to be careful here is just changing the loss naively won't necessarily avoid our conclusions. I think people are going to have to be clever about how they change their loss. Okay, and now this is probably the biggest caveat. It's important to highlight that both Barren plateaus and in places, but not everywhere, our notions of simulability are average case notions. This is why I've been throwing around the word typically quite a lot, quite loosely. Okay, so a Barren plateau, even though you have with exponentially high probability over the landscape negligible gradients, it is possible to have substantial gradients in exponentially small subregions. In parallel, simulation in certain cases, I'll come back to this in a second, might also not be possible in exponentially small subregions. And now if these two things combine, if we have some region with gradients that we can train in and some region that we can't simulate, then suddenly things do get very interesting. Okay, so to spell out this point, let me dive into some details I skipped earlier. Okay, so there are two different notions of simulability that we consider in our paper, both an average case and a worst case notion. So we'll say that an algorithm can simulate loss functions if it can implement a function L tilde of theta that approximates the loss up to ever epsilon. In the average case, we need this to be that on average over theta, the distance between the difference between our true loss and our approximated loss is less than epsilon. And in the case of worst case simulability, we require that this difference is less than epsilon for all theta. So average case on average for all theta, worst case just for all theta. Okay, and then I've been talking about these polynomial subspaces. Let me also draw a distinction between different types of subspaces. So we can consider proper subspaces. So this is a proper polynomial subspace is a subspace that is strictly polynomial in size. Whereas an effective subspace will be one that is effectively polynomial in size, but can have small tails, so small weighted terms that have small contributions outside of a polynomial subspace. Okay, so that's one axis we can look at. Another axis we can look at is whether it happens, whether the Heisenberg backpropagated observable lives in a proper subspace or an effective subspace for all theta, or just with high probability over theta. So note these, in theory, you can have 4 different options here. So you can have a proper subspace for all theta or a proper space with high probability over theta, and you can have an effective subspace for all theta or an effective subspace with high probability over theta. In fact, in our investigations, we find that these things are perfectly correlated. So we're either looking at a case where our problem lives in a proper subspace for all theta, or we're looking at a problem where our problem lives in an effective subspace with high probability over theta. Okay, so what do we have for the different cases I was looking at earlier? So most of these cases, so namely ones where you're basically working with shallow depth circuits or highly symmetrized ansatzer, live in proper subspaces. So you are in a proper subspace for all theta. So you are strictly in a polynomial subspace. But there are 2 cases, quantum convolutional neural network and small angular initializations, where the problem is not in a proper subspace, but rather you are in an effective subspace. So that is when you look at the backpropagated observable, nearly all the terms that have substantial weights are in some polynomial subspace, but there are some small tails outside of that polynomial subspace, and for some values of theta, these tails can be bigger. But on average, with high probability, you are in some effective subspace that is polynomial. Okay, so what does this mean for simulation? So in all the cases where you're in a proper subspace, then you can have basically worst case simulation for all theta. But in the effective subspaces, so in the special case of quantum convolutional neural networks and small angle initializations, then you can only simulate with high probability. So you can simulate with high probability over theta in this probability distribution. So you can simulate with high probability and to a high degree of approximation, but there is still some wiggle room that there'll be some parameter values where something interesting could happen that you can't simulate. Okay, so this is just backing up the claim I had before. So in all cases, Barren plateaus don't preclude the fact that you can have some gradients in exponentially small subregions. And in certain cases, our guarantees of classical simulation also have this wiggle room. So namely the case of quantum convolutional neural networks and small angle initializations. So this raises the question of whether there is potential offered by warm starts. So a warm start would be the case where you somehow try and cleverly initialize and explore the exponentially unlikely, but nonetheless existent region where you have small gradients, substantial gradients. Okay, and now I think a really important caveat to add here is that we need substantial gradients, not just around our initialization, but also along a trajectory to a reasonable solution. So for example, these small angle initialization papers show that you can have substantial gradients around identity. Fine. But for interesting problems, do we expect our solution to be near identity? Probably not. And if our gradients are vanishing with probability exponentially close to 1 over the whole landscape, how likely is it that they will find that there is gradients not only close to initialization and the solution, but also along a nice trajectory to get to the solution? So I think most disagreements in the community now about the barrier posed by bound plateaus boil down to answering this question. And I don't think anyone really knows the answer. So I think naively, just sort of looking at the maths, looking at the probabilities, it would seem that it is pretty unlikely that if you find a region with gradients initially, you're also going to find gradients that take you all the way to the solution, given we know that with exponentially high probability, the landscape is flat. However, classically, things do seem to work out quite nicely. Classically, optimization works in all sorts of regimes that we don't expect. And so you can also push back against the intuition posed by the maths and say, maybe things will work out. But yes, I think crucially, no one's got a crystal ball. No one knows the answer to this question right now. But we're interested in trying to address this question. And I think if you are going to try and come up with clever warm starts, I think iterative approaches where you somehow start and follow a solution as you go along are one of the most promising strategies. And so in this paper here by two actually great Spanish students, both Catalan students, Ricard and Mark, we investigate this possibility. So we show that actually around a warm start, you can have substantial gradients. And then we try and tackle some of these questions about how likely it is that you will have substantial gradients along a whole trajectory. But there are, anyway, check out the paper if you're interested. Okay, but anyway, key question. What are the odds of having substantial gradients, not just around initialization, but also a trajectory to a reasonable solution? I said just staring at the math you would think is unlikely, but there is always the hope offered by classical machine learning. So this is Marco's meme. He is not so optimistic about the potential offered by warm starts, but I really think it's an open question. So yeah, many arguments were had in the making of this paper and continue to be had on a daily basis. So the final caveat I want to end on, which is sort of the caveat that my last point led to, is the who cares about proofs questions. So everything that we've been discussing so far relies on proof of absence of bound plateaus. We say that if we can prove the absence of bound plateaus, then we can identify some polynomial region which we can classically simulate or classically surrogate. But it could be the case that we heuristically find large gradients somehow by doing larger implementations when we eventually have devices that are good, but we can't find any identifiable polynomial subspaces. And then, yeah, the people who like this line of thought argue that this is analogous to the classical case. So classically, machine learning works out way better than we ever expected. I think there are two things to remember here. Well, multiple things, but I'm going to focus on two. Firstly, precision is much more expensive quantumly than classically. So classically, you just add another bit and this doubles your precision. Quantumly, you've got to work really hard, running more and more circuits, taking more and more shots in order to increase your precision. So that's the first point. And if we have low precision measurements, this means bound plateaus and flat gradients are so much more of an issue. Classically, you can have flat gradients, but just ramp up your precision and then figure out ways of navigating them. So that's point number one. Point number two is that the fact we have classical machine learning that is so successful means we have quite a hard bar to beat, particularly when it comes to surrogating versus running the VQA. Because the advantage of surrogating is all of the optimization is done classically. You can then use back propagation and throw your entire arsenal of classical ML at it. And so it seems likely that in many cases then that the classical surrogating methods could be superior. So yeah, in the quantum case, we don't just need to be successful. We don't just need the things to work better than planned. We need things to work better than we can do with the help of classical ML. So does this who cares about proof response actually solve anything? I don't know. I think it really depends on your faith in optimization, your faith in optimization just working out when we can't prove things. And I think this is a personal opinion, whether you take it as sort of akin to blind faith and you're pessimistic, or whether you decide to pray to the gods of classical machine learning and be optimistic. Okay, so that is everything I wanted to say. In conclusion, I have made 3 claims. First claim is that bound plateaus arise from recursive dimensionality. That was claim 0. Claim 1 is that provably bound plateau-free architectures live in classically identifiable subspaces. And claim 2 is that problems in known polynomial subspaces, i.e. the ones that we can prove are provably BP-free, are classically simulable or classically surrogatable. So they're classically simulable if your initial state is classical and your measurements are classical. They are surrogatable if you have quantum initial states and quantum observables. So those are the sort of the factual claims, and then there are all sorts of caveats and future opportunities in terms of where we go from here. Thanks for listening.
Thank you very much, Zoe. Really was a very nice and interesting seminar. And I opened a couple of 15 minutes more or less about questions. If you want to participate, you can use the chat because we can now open the microphone. So use the chat. In the meantime, because usually the people don't want to ask in this kind of seminars, I have one question because I think that one hypothesis that you have in your paper, well, in fact, you saw it is these are classical quantum parametric circuits without intermediate measurements. This means that you are using something from the beginning to the end with usual unitary gates, but you are not measuring any qubit during the process. Am I right or not? Because
so quantum convolutional neural networks do measure throughout.
Yeah, for example, the quantum requirement networks, yes.
So we can handle quantum convolutional networks. So
yeah.
So effectively we just generalize our U of theta to a channel of theta, and that can handle the mid-circuit measurements. And so, yes, our argument also applies to those cases typically.
Okay.
So I think the only case where people have proven absence of bound plateaus in those using mid-circuit measurements would be for quantum convolutional neural networks, and that fits under our assumptions. So we can show that actually for quantum convolutional neural networks, you live in a polynomial subspace. You're basically living on log n adjacent Paulis, and so you can just project down onto that subspace and measure.
Okay. Okay. Javier, Joe Bravo writes the ham.
I think you can ask now if you activate your microphone, Joao.
Can you hear me?
Yes.
Yes.
Cool. All right. Thanks for the talk, Zoe. I have a couple of questions. Maybe the first one a bit basic, but and not really related to this topic. In the beginning, when you were mentioning that very entangled states, initial states, can also cause Barren plateaus, you mentioned that the quantum state should follow an area law. So what does this exactly mean? Following like a volume or area law?
So the definition, so there are different definitions of area law and volume law in the literature. The one I have in my head that I'm referring to is if the distance between the reduced state and the maximum mixed state vanishes exponentially, then you're following a volume law. So that is if you're exponentially close to maximally mixed. But if you are only polynomially close to maximally mixed, so the distance between your reduced state and the maximally mixed state is only vanishes polynomially, then you obey a area law. So it's how close you are to maximally mixed when you look at the reduced state.
Okay, thanks. And regarding this final paper you mentioned, is it possible to give an overview of how do you actually find these subregions with large gradients?
Okay, yes, so we here are looking at a really special case. So we're looking at a proposal for quantum simulation, where what you do is you're basically iteratively compressing your trotter circuit. So you start with an initial state, you evolve it for a short time forward under some trotter evolution. Then you have some parameterized quantum circuit, and your idea is with that parameterized quantum circuit is you're going to try and learn a more compressed version for doing that initial trotterization. Once you've learned that, you then do this again. So you take your initial state, you then do one trotter step forward using your learnt circuit, and you use a trotter step to propagate forward another delta t in time. So now you've got evolution for basically 2 delta t in time. And then you're going to take your parameterized quantum circuit again, and you are going to try and learn a compressed circuit now to implement 2 evolution steps forwards in time. So this is not a new proposal. There's been about 6 or 7 different papers that have been investigating this, but we've done an analysis of its trainability. So the key thought is, if you start off with a trotter step for a short time evolution, then your initial time step is going to be close to identity. So then you can start with your parameterized quantum circuit, initialize it close to identity, and then sort it. Actually, for that first step, these small angle initialization results that I referenced earlier already work. What we've been looking at more is later time steps. So for later time steps, you'll start near a solution because you're going to initialize close to your solution for 1 time step, and then you've just got some small extra time step forward. So the point is your unitary doesn't change. You're trying to learn a unitary now for 2 time steps, having already learned a unitary for 1 time step. And assuming your time step is small enough, you shouldn't be too far away from it. Your initial solution shouldn't be too far away from your new solution. So by tuning delta t and by tuning the region you're looking at, you can basically ensure that you're within your narrow gauge. So you have this landscape that is largely flat, but around a solution, you've got a minima. And as long as you start within that minima, which you can do by making sure your time step isn't too big, and then as long as you initialize in a small region, you can basically argue that you do have gradients in that region. So that's sort of the big picture of what we're doing. Then there are all sorts of caveats, because though we can guarantee you'll have gradients in that region, or in a region around your initialization, all sorts of funky things could happen as we go to bigger problems, whereby the minimum could jump away from the region in which we have guarantees to some completely different part in the landscape. But generally, the sort of big picture idea is you're taking a perturbative approach. You're keeping your solution warm the whole time, and you're trying to never stay too far away from the solution. So you just have a simpler optimization problem at each step where you're initializing within the narrow gauge.
But okay, so maybe I'm not understanding something, but doesn't this assume that we somehow have know more or less the solution already?
No, because so you do know a solution. So a solution is just implement the original trotter unitary. But if you do that, your circuit is going to grow linearly in time. The idea is you want to have a much shorter depth circuit, one that doesn't grow linearly in time. So you're trying to learn a circuit that doesn't look like the trotter unitary, because the trotter unitary would have to grow linearly in time. You're trying to figure out a circuit that is much shorter depth. And so we don't know a circuit that looks like that. So we know a solution, but we don't necessarily know the solution within our ansatz. We don't know the solution for the ansatz that we have decided to use in order to try and reduce the depth of the circuit.
Okay. Okay. Yeah. Thanks.
More questions? Raise your hand. In the meantime, do you think that that optimizers that are not based on gradients can work for this kind of circuits?
No. So as I said way back, it's probably too many slides to go back there. You can frame these arguments both in terms of cost variances and cost gradients. So even if you don't have gradients, any optimization method is basically going to work by trying to figure out cost differences. And if your landscape is very, very flat, then you're still going to have issues. So it's not just gradients. You need cost differences. And if the variance in your cost is exponentially small, you don't have substantial cost differences.
Okay. Any other question? If not, sorry, thanks a lot.
Thank you.
It was an amazing seminar, and I hope that the people can contact. Oh, there's one hand. No. I hope that we can meet in the future in another seminar and with nice results for your work. Congratulations and thank you. For the people, remember that we have these seminars periodically, and the seminars are organized by the TalentQ program, and you have the web talentq.es. So visit it periodically, and if you want to propose something, we are open to try to analyze your request and try to organize things specific for your request. Thank you very much for attending, and I hope to see you soon. Bye.
Thank you.